Okay, it's upon recording. So good morning, students. We'll start with photo detectors today. But before that, just a quick recap of what we have already done. So we have already discussed about sources, both LEDs as well as lasers. So in the last two lectures, we had discussed about lasers, how the lasers operate, with the absorption and spontaneous emission and the stimulated emission. So we have discussed about that. And then we discussed the concept of population inversion, which is very important. The threshold conditions or the resonant conditions for the laser that we have discussed. We have discussed the types of the lasers. So it will be very important to know the types of these lasers. Okay, so we have the Fabry Perot laser and we have the distributed feedback laser. So both operate almost in the same way using what is known as an optical or a resonant cavity, where you can see on the diagram that the light which hits the first mirror comes back to the initial mirror. So it travels a certain distance and we expect this light to be amplified in that case, right? So it also shows you the structure of the Fabry Perot laser. So you can see that the beam, the light beam is very directional. It is very sharp, and this is the advantage that you get from a laser when compared to an LED. Okay. So then we move to we have seen how the the intensity of the laser will look like, and you can see it is very sharp in comparison to the LED, right? Okay. So then we looked at the lasing operations, the equations. So I'm not repeating that. That mathematics is already done. What are the modes and how the characteristics look like, and the spectral width gain. So this mathematics we have done. We've solved one numerical also, right? So overall, we have done the optical sources, LEDs and lasers. And what we have understood from that concept is that the LED can be used for smaller distances. It will provide efficiency, whereas if we want to transmit for longer distance, which we want to do most of the time, then we should be using a laser. Of course, a laser has its own issues as well in terms of cost and what is known as speckle noise, which we'll deal later. But overall, it provides more efficiency, right? So now, having done this optical source, now we want to talk about optical detector. Okay, so before we go into that, I want to uh, separate out what is an optical detector and what is an optical receiver. Okay, so like I told you in the last class, mostly people use these words interchangeably. Okay, but to understand the difference between the two, let's take this block diagram. So let this be a laser. Okay, the source, and this is the current which is falling on the laser. So I'm going to denote it as E minus, that is electrons. And let this laser give us light. So I'm going to write HF. And then we have the optical fiber through which light is going to propagate. Okay. Now at this end, we need what is known as a detector. Okay. If I want to be more specific, optical detector, which will get photons as input, and its job should be to convert this back into the current, that is E minus, right? So this is an optical detector. Why? Because it is detecting these number of photons. So as many photons will fall on this detector, correspondingly the number of electrons will be generated, right? And more the number of electrons, obviously more is going to be the current, right? Now once these electrons are generated, once these electrons are generated at the output of the detector, now this system, I'm going to dot it. Okay, now this system here just becomes a normal electrical system. Why? What happens in the electrical system? Current will fall, or the number of electrons will be following on that, and it needs to detect how many. It needs to find out whether those bits are in error or are they not in error, right? So this dotted portion where you will have electrical system going on, that is known as the receiver. That is known as the receiver. So this receiver we will see will have an amplifier. It could, for long distance, it will have what is known as an equalizer, right, which is basically a filter, and then it will have its own integrator, which will decide whether the bit is more than a threshold or bit is less than a threshold, and it will decide on the bit which is 0 or 1, right? So we will be discussing this receiver part here, the electrical receiver part here, and this is where you deal with things like metrics like bit error rate or signal to noise ratio. Right? So we'll look at that when we talk about receivers and what components or devices comprise of that. But right now our focus is on the optical detector. Right? So at the output of this optical transmission light, you must have some receiving device, right? And this detector, which is going to interpret the information in the form of optical signal, that is light. Right? So this is basically the receiver, that is the photodetector. That's why it's called a photodetector. So the job of this photodetector will be to sense this power, right? This light power which is falling on it, and it needs to convert it into the corresponding electric current or the current in general. Now we must note that this optical signal is going to be weakened, right? Why? Because it is going to travel some distance L, right? So the optical signal which we get here, this number of photon, this is going to be weakened when it comes at the output of the fiber, right? So the requirement from the photodetector needs to be very, very high, right? So we need to understand here the HF, number of photons, is very high here at the output of the laser, but the corresponding photons which we get at the receiver are very, very low because you have already traveled some distance L here, right? So the requirements, the functioning of this photodetector is very, very high. We require this photodetector to be very, very efficient photodetector, right? So in terms of performance requirements, right? In terms of performance requirements, what do we need? We need minimum addition of noise. Okay, of course, photodetector has no role to play in that because noise is random, so we don't know. But we expect that it by itself it adds minimum amount of noise. So we have already seen in laser and LED that the device itself has some errors, right? So we are expecting this photodetectors to have minimum of such errors in themselves because outside the noise is going to be very high. Like the LED and the laser, we require high response or high response time. So whenever light hits this detector, we expect it to just give out the current at the output, right? Another thing that we need is it should have enough bandwidth to accommodate large data rate. Large data rate. Why? Because the fiber is providing us very high bandwidth. So this photodetector should also operate over a range of frequencies so that we can get this high data rate. Okay. The other aspects in terms of the device would be it should be insensitive to temperature. So it's like a resistor, right? If you hold a resistor in the hand, if it is 1 kilo ohm, because of the change in the temperature, because resistance has this equation with K into T temperature, you'll see that the resistance actually will not be 1K. It could be a little lower or a little higher, plus minus, right? So like that, devices, components are sensitive to temperature. We expect this photodetectors to be insensitive to temperatures. It should be compatible with the corresponding optical source. Means the same detector should be in a condition to work with LEDs as well as that of laser. And of course the other aspects we need is it should be have reasonable cost, and it should be able to operate for longer time. and it should also be reliable. So I'm just going to write here a word which takes care of all of this, which is reliable. So it should be reliable, right? So in this, with all of this, the detectors which are mentioned in your syllabus are two types of detectors. So I've already put the diagram of one of the detectors that you can see on the screen, right? So the two detectors which we need to do, let me scroll up and write here so it will be clearer. So the two detectors which we have in the syllabus, one is the pin photodetector and the other one is an avalanche photodetector, or in short APD. And I've already told you avalanche is an English word which means multiplication, right? So in the APD we expect this current to multiply with large numbers, right? So we look at the APD a little later. It is an extension of the pin diode, but let's first try and understand the working of this pin diode. So I've already put the diagram. These diagrams are there in the notes already. So I'm just going to explain you the important points and how these diodes are going to function. Right. So we'll start with the pin diode. So the device structure basically will consist of the P and N region. So you can see the diagram on the right. This is the diagram for the pin diode, or let me be specific, pin photodetector. Okay, so it consists of the P and N region, and this is separated by a very lightly N doped intrinsic region, right? So you have the P structure, you have the very lightly doped or lightly N doped intrinsic region, and then you have the N region. Right? So let us understand what happens or how this pin detector works here, right? So this working is shown here on the right hand side, the second diagram. So this is the working. Just let me draw a line because there is a diagram below it, but that is not of the pin diode, right? So for the working part, there are two cases how this is going to work. So in normal operation, so when we have what is known as the normal operation, so you apply a sufficiently large reverse bias voltage. You can see that the PN junction is connected in the reverse bias. So in the normal operation, we given a very large or sufficiently large reverse bias voltage across the device, and so that this intrinsic region, the I region, this is going to be completely depleted of the carriers, right? So what is going to happen is the intrinsic N and the P carrier concentration will be very small in comparison with the impurity in the region, right? So what happens is, now when you have a photon which is incident, then you will have an energy greater than or equal to band gap energy, right, which we need to supply. And once this energy comes in because of the incidence of the photon, you can see on the diagram. So when this photon is going to impinge, when it hits, so the device will be able to meet this band gap energy, right? And once that happens, the photon gives up its energy, and this is going to excite this electron to from the valence band to the conduction band, right? So that is what is happening. You can see here that once the photon will hit the electron which is in the valence band, which is here, will now jump up and go to the the conduction band, right? And once that happens, then the conduction is going to start. So this process by which we are able to meet this band gap energy, this generates the electron hole pairs, and these electron hole pairs are what are known as photo carriers. So this is an important word. So these will be nothing but the electron hole pairs. Okay, these will be generated and they are known as the photo carriers. Now these carriers will be available to produce current, right? And when a bias voltage is applied across the device, so we have already applied the bias voltage, reverse bias voltage, and because of that, now the current is going to start flowing, right? So now this number of carriers, this is going to be controlled by how much impurity you have, what is the concentration level of impurity elements, that we have added inside this material. So that intrinsic layer will decide that. So now this photodetector is designed such that carriers are generated in the depletion region, and most of these incident light will be absorbed. So all of this is going to happen in that I region there. So this region here, the I region, is going to be very important. How many number of, how have you doped it, how much light is going to be absorbed in there, all that needs to be known there. So now this high field, the voltage which we have applied, is present in the depletion region, and this will cause these carriers to separate, and they will collect in the reverse bias junction, right? That is the basic operation of the PN junction, and these will now give rise to the current or the flow of electron, and this kind of current flow is known as photocurrent. Photocurrent, right? So this is flow of current, okay? And it's called as photo. If I split this word, it's called as photo because it is happening because of the photon here impinging or striking the electron there, right? Same with the carriers. We already know what carriers are, but they are photo carriers because of this photon hitting the electron in the valence band, right? Now, as these carriers are going to flow in the material, some electron holes are going to recombine, and then they are just going to be going to disappear, and because negative and positive are going to meet each other, and the charge carriers, the electron and holes, they will move a certain distance, and this distance is known as diffusion length. This distance is known as diffusion length. Okay, so this is an important concept of diffusion length. We'll just talk about the diffusion length in a little bit. Okay, and the time that it takes for these electrons and holes to recombine, that is known as carrier lifetime. Carrier lifetime, right? So it's a simple operation. Photon needs to hit the electron in the valence band. It will provide enough energy equal to or greater than band gap energy of the material, and the electron will move to the conduction band. Because we have applied bias voltage, the reverse bias voltage, all of these carriers will start moving towards the junction, and once they start moving, they will cover a distance which is known as diffusion length, and as they are moving, there is a flow of these carriers, and that will generate the photocurrent. But once they are moving, there is possibility that these electrons and holes of opposite charges are going to recombine, and slowly your current is going to start to lessen down or disappear, right? So the time for which these carriers will be there, and they take the time to recombine, that is known as the carrier lifetime, right? So next we want to see how these carrier lifetimes and the diffusion length are related to each other. So that is shown in this diagram here on the right. This diagram, it's an important diagram. So let us define few terms and then we'll see how they are related. So let this carrier lifetime, let this carrier lifetime, let this be denoted as tau n and tau p, right? These are the subscripts are there for the electron and the hole. So n is for the electron, negative, and p is for the holes, that is positive, right? So the lifetime and diffusion length, this is related as, so if you have Ln, the diffusion length of the electrons, this is given as dn tau n raised to half, and Lp is similarly given as d subscript p tau p raised to half, where dn and this dp, these are known as diffusion coefficients. Diffusion coefficients, of electrons and holes. These are known as the diffusion coefficients of electrons and holes. So we don't have any numericals based on this, but this is just the information required for showing how the diffusion length and the carrier lifetime are connected to each other, right? So what you see on the right hand side, the diagram which I've started, is the relative power level, and what you also see on the x-axis is this x, and that x is nothing but what is the power level after a certain distance, right? So we can see that initially the power is p naught, right? And at this point or at zero, there's complete power. But as you are moving the distance, right, we reach a point w here, right? We reach that point w, and at that point you can see that the power has exponentially decayed, right? So the p of w, you can see at this point, is much lesser than that of the initial power, which is that point there, right? So that is what happens with the length, that is the diffusion length. The power is going to reduce because the electrons and the holes are going to start to recombine with each other, right? Because positive and negative charges are there, right? So the diagram, the second diagram, is just for reference. It shows you the absorption coefficient D over a wavelength for different materials. Is just for your reference. No need to memorize this. It shows how D, the optical absorption coefficient, is dependent with the wavelength for the various materials, right? So what is important for us is to understand a few of the other aspects of photodetectors, right? So let me remove these diagrams. These are for let us first do the mathematics behind it, and then we'll go ahead and do the photodetector, the avalanche photodetector. Okay. So this diagram is very important. We'll cover this diagram a little later. So move this. So all these diagrams are available in the notes. You can refer to the notes. Okay, I'm explaining the important points. Okay, let me move this also. This belongs to APD. So what we want to do is to find the what is known as the responsivity of a particular photodiode, and then we want to calculate its quantum efficiency as well, right? That is what we want to do for a photodetector. Okay, so let us start with that mathematics. So any semiconductor material, because these are all semiconductor based diodes, any semiconductor material uh, can be used only for limited wavelength, and that we have already calculated. You have E equal to HF, which can be written as HC by lambda, which will imply that lambda, the maximum lambda that we have, or the upper cutoff wavelength, is HC divided by EG, where this is the band gap energy, and H into C can be evaluated, it's Planck's constant, into the speed of light, and that gives a value of 1.24 divided by EG, which is in electron volts, right? So this is the wavelength dependence of any semiconductor material over a particular wavelength. So for example, for silicon, this lambda C will be 1.06 micrometer. If we take a germanium material, the lambda C turns out to be 1.6 micrometer. Okay. So from that, it is clear that longer wavelengths, photon energy is not sufficient, right? For longer wavelength, energy will not be sufficient to excite electron from valence band to conduction band. But the thing is, we want to operate at longer wavelength, right? So if I operate at 1300 nanometer, right, the photon energy may be sufficient to excite this electron from valence to conduction band. Then I will get the conduction which I require. But when I obviously want to operate at 1550 nanometer, right, because that's where we can use laser, we can use APD and various other components. But the problem is that the energy may not be sufficient to excite electron from valence to conduction, right? Also, at lower wavelengths, the response is found to be much better of these photodetectors compared to the longer wavelengths, right? So lower wavelengths have advantage in that sense, right? But obviously we want to operate at a higher wavelengths, right? So let us see how we can calculate the various characteristics of any photodetector, any pin photodetector. And here we want to calculate what is known as the quantum efficiency, and the second is the response time. So we want to calculate these aspects when it comes to uh, characterizing any photodetector, right? So let us see how we can do that, and then this will be important in calculating the signal to noise ratio a little later, right? So we want to calculate that, and then we want to also see what is this responsivity, right? So in general, what is this quantum efficiency? Okay, so in general, let us first do quantum efficiency. It is denoted as QE, this quantum efficiency, and it is denoted as eta. This is nothing but number of electron hole pairs generated divided by the number of incident photons. Okay, so this ratio is similar to what we had done in LED and laser. But if you remember, there the numerator is same, number of electron hole pairs generated, but it was number of electrons, incident electrons. Why? Because in the source, the input is the electrons, and we want to see how many photons are going to be generated. Here it is the opposite. Here we want to see how many electrons will be generated at the output when there are certain incident photons, right? So this ratio can be mathematically written as number of electron hole pairs generated will be some I. I'll denote it as IP because it is photocurrent. So IP divided by Q, which is the charge on the photon, divided by the number of incident photons, where you'll have number of incident photons as P in, that is the input power, divided by HF, right? So if you write this equation properly, this will be IP photocurrent divided by Q, or let me write P in first. So P in into Q, and HF comes here. So I can rewrite this as HF IP divided by Q P in, or if you want to write it in the terms of power, P in will be HF IP divided by Q eta. Right? So this is an important equation. This is an important equation. Okay. Let me get these diagrams down. Okay. So we expect this eta to be as high as possible, right? So if a photodiode has, if 100 photons are created, if 100 photons create 30 to, let's say, 90, for example, electron hole pairs, then this eta is going to be between 30 and 90, right? So this eta is what is known as the responsivity. This is what is known as the responsivity. Okay. In some books, sources, they also denote it as R. Okay, responsivity. So to achieve high quantum efficiency, in general, we require this depletion layer to be thick so that it can permit lot of light to be absorbed, and therefore electrons can move from conduction band to the to move from the valence band to the conduction band. Okay. So another way of writing this responsivity, right, or the response time in general is you can have responsivity R related to eta quantum efficiency, and this is nothing but R equal to IP by Pn, where IP is the photon current and Pn is the input power, and you can have this as eta Q divided by HF. So this is another way in which we can write the responsivity, and responsivity is always expressed in percentage. Right. So the diagram which we were seeing up here is showing us responsivity in terms of wavelength, right? And we can see that the quantum efficiency, which is specified on the right hand side here, this quantum efficiency is not constant at all wavelengths, right? So it's not that you operate at any wavelength and you will get the same quantum efficiency. It is very much dependent on wavelength. You can see, if you see this material here on the right hand side here, you can see that its quantum efficiency keeps responsivity keeps increasing to a particular wavelength and then dies down. So if I just draw the peak value here, it comes to somewhere around 1.6 or so, right? Whereas if you take this material here, its peak value is somewhere around 1000. Okay, so this quantum efficiency and responsivity, they are dependent on the wavelength because it is going to vary with photon energy, right? In general, beyond the cutoff wavelength, the responsivity is going to decrease much rapidly, because the photon energy, it becomes less than what is required to excite electron from moving from valence band to the conduction band. Okay. So these are some of the basics of the pin photodiode. Of course, some more information is mentioned in the notes as well, but they are more theoretical, but these are the important points. Okay. So there are numericals based on the responsivity which come in, but in general I have not seen separate numericals for responsivity. This will be used more when we calculate the signal to noise ratio. So we'll see that you'll have this ratio as signal power divided by noise power, and this here in the signal power we'll be using the responsivity to calculate the signal power, right? So if you have 100 say photons hitting the photodetector, the pin photodetector, obviously 100 electrons are not going to be generated. There are going to be some are going to recombine and light is not going to be generated. So there is some difference in the input and output in that sense, and that is what will be calculated by the responsivity, right? So in general, the silicon ones give you about 70 to 75% of responsivity compared to that of germanium based, but germanium based are obviously a little bit more costly. They are not generally used that much. Okay. So this is some of the basics of the pin photodetector. It operates in the reverse bias mode, as we have just seen. Okay, so I've given you the equation for eta, and I've also given you the equation for R. So that is quantum efficiency as well as the responsivity. And we have seen how these two are related to each other. We have seen that they are not constants. They are, it's not going to be a constant scenario for the responsivity as well as quantum efficiency. It's going to depend on a number of factors, right? More specifically, it is going to depend on the wavelength where we are operating. right? So based on this, we could have some numericals. They are very simple ones where you can just calculate, use this equation to calculate the responsivity. But I'm more interested in calculating the signal to noise ratio later on, where we can use this equation to find the signal power. Okay. So the simpler ones where we just have to plug in eta, q, h, and f to find r. Those are very simple. We can use a calculator to find. So I'll leave those numericals for now, and we'll pick this up when we are doing optical receivers, and there to calculate signal to noise ratio we'll be using that. Okay. So so this was about the pin photodetector. There is another detector which is mentioned in your syllabus, that is known as the avalanche photodetector. And after doing that avalanche photo, it is same as the pin detector. After doing that, we could solve some of the numericals, and then we'll move to the optical receivers. Okay.